our second talk is still on information flow security, but this time is concurrent programs, and Marco Eilers will be giving the talk.
Right. Thanks for the introduction and thanks for coming. So my name is Marco Eilers. I'm going to tell you about CommCSL, which is a new logic for proving information flow security for concurrent programs using abstract commutativity. So our goal is to prove information flow security, not to quantify how much we're leaking. We want to prove that we're not leaking anything at all. So the property that we want to prove is non-interference. The idea is, as before, we have a program that has a set of secret inputs, high sensitivity inputs, we call them H here, and a set of low sensitivity non-secret inputs, we call them L here. And we want to prove that the output values, the publicly returned visible output values returned by our program don't tell us anything about the secret input. And the way we're formalizing that is by demanding that the publicly visible returned value is completely independent of the secret input. So to make that more formal, we can say that whenever we execute our program twice with the same non-secret input but different secret inputs, we should get the same result because the result is independent of the secret inputs and thus the only thing we're changing. So this program that I'm showing you on the left obviously doesn't have this property because for different values of H, we might see results 1 or 2. But if we fix it and, for example, change the other assignment to also be res gets 1, now this program always returns 1 no matter what H is, so this is one that we would accept. Now obviously, and as we've already heard, result values aren't the only way to leak secret information. We could have like timing side channels, for example. Here's a program that, depending on the value of the secret input H, does more or less work and probably will take longer or, well, less time. So if we have an attacker that can observe timing, then they might be able to conclude something about H. Now, while reasoning about output values is at least conceptually somewhat simple, it's clear what to do, reasoning about timing in practice is really, really difficult. And the reason is that timing is, at the end of the day, influenced by the hardware that we're running on, by the compiler that we're using, and all of these are really, really complex, right? We have complex cache hierarchies, speculative execution, and whatnot. So if we want to be really sure that we don't have a timing side channel, that's quite difficult. Now, the good thing is, sometimes we don't care about timing, and these are really, you can see them as two different problems that are separate from each other. Now, that is the case until we have concurrency, because concurrency has this unfortunate property that it can turn timing channels into value channels, and I'll show you how. So here's another simple toyish example. We have a program consisting of two threads, a left thread and a right thread. They both start by executing a loop that counts some variables I and J from initially 0 to, in the left case, H, which is our secret input, in the right case, 100. Then after those loops, they both assign different values to the shared variable shared, and then we join the threads and return that value. Now, each of these threads independently doesn't do anything bad, right? The left one doesn't leak H in any meaningful way. But now, if we execute this program, the following happens. If we execute it with H having a really low value, like 4, then the loop in the left thread will terminate quite quickly, and the assignment of 6 to shared in the left thread will happen early. And will probably happen before the assignment of 7 in the right thread. So in a sense, the assignment in the right thread will win out and overwrite the other one, and we'll see the result 7. If, on the other hand, we pick a really large value for H, like 300, then the loop in the left thread will take longer, and its assignment will happen later and will likely see 6. And I'm saying likely because this depends on scheduling, right? But clearly we're leaking here something, at least probabilistically. So this is something we want to prevent. And if we zoom in a bit on what the problem is, what's really happening is this. We have secret input, a secret value, that influences the execution time of a part of a program. That, in turn, influences the order of modifications of shared data, namely the order of the assignments to the shared variable here, and that influences the final result value. Okay, so this is how timing channels can kind of turn into value channels. So from now on, for the rest of the talk, we're going to try to prove information flow security against an attacker that can't see execution time directly. So they can only observe the final results that we're returning. They can't see our memory in intermediate states or timing. But because of this effect that I've just shown you on this toyish example, obviously they might still see value differences as a result of timing differences. Okay, so this problem isn't new. People have known about this for a while, and there are actually many solutions out there. And they broadly fall into two categories. And I'm really summarizing quite broadly here because it's a lot of existing work, some of which proves different or stronger properties, but broadly two categories. The first one says, well, okay, then let's just not have shared data, or at least let's not have unordered modifications of shared data. So they reject this program because two threads modify shared. And that's sound, of course, that solves the problem, but that obviously also rules out many programming patterns that we would like to be able to use. The second one is to say, well, okay, then we can't have secret values influencing execution time of parts of the program. So they would reject this program because the loop in the left thread has a secret dependent runtime. And that also works conceptually, but again, now I'm reasoning about execution time even though my attacker can't directly see it. Right? So this is going to make things really, really difficult. So our goal in this paper, and what our new technique achieves, is to provide a new way to modularly reason about values and value sensitivity in concurrent programs without having to reason in any way about timing. And I'll show you a variation of this example to kind of motivate our key idea. So this is almost what you've seen before, except now we initialize the shared variable with our non-secret input L. And instead of just assigning 6 or 7 after the loops, each of the thread atomically adds 6 and 7. Okay? So now all existing modular compositional reasoning techniques would still reject this because we still have shared data and we still have this loop with the secret dependent runtime. But if you think about what the output of this program will be, it's always L plus 13. Right? Because at the end of the day, we can still have these modifications of the shared variable in different orders, but that doesn't influence the final result in this case, because both of these are additions and additions commute. So this is the first key idea of our approach. The secret-dependent order of modifications of shared data does not influence the final result if these modifications commute. And this is what we want to build our verification technique on. So basically in this diagram on the right, we're targeting the other arrow. We're allowing secret values to influence the execution time because that's really difficult to prevent anyways. That means, for example, we don't have to forbid branching on secret values or anything like that. We can be quite permissive there. And instead, we impose other proof obligations that make sure that the order of modifications doesn't influence the final result. Okay. That means we can accept this program here, but we'd still reject the previous one where we just assign 6 or 7 because assigning 6 and 7 doesn't commute. So we've formalized this idea in a logic called CommCSL. I'm not going to show you any of the details of CommCSL. Instead, I'm going to show you on a high level the proof obligations that we impose on programs that we verify. So here, these are supposed to be 2 executions of the same program that differ only in the secret inputs. So whenever something here is different in the 2 executions, that's because it's possibly secret dependent in some way. If it's the same, that means it's not influenced by the secret. So now at some point in these executions, both programs start spawning some threads and share some data structure to be used by those threads concurrently. And that's like that point is supposed to be the block at the top. Now at this point, we impose the following proof obligation, namely that at this point, the shared data structure must have the same value in both executions, which means the value does not depend on a secret. So after this, in both executions, the threads will perform some modifications of the shared data. In this case, they're adding things, 1 and 5 and 3 here. And for all of these updates, we require that they commute. So in this case, that's fine, because this all additions, they commute. But for example, if it was additions mixed with multiplications, we would reject the program. Now, the third proof obligation is that both executions perform essentially the same updates, just maybe in a different secret-dependent order. So if the left one adds 1, 5, and 3, then the right one also needs to add 5, 1, and 3. So in this case, we can match them up 1 to 1, and everything's fine. But for example, if the right execution would have another addition of 5, And the fact that it's there in the right one and not in the left one means this is dependent on a secret, right? This is, again, something we would have to reject. So those are our three core proof obligations. And if we can prove all of these, then we get to assume that in the end, after all concurrent modification is done, the shared data structure will have the same value in both executions, meaning that it's not influenced by secret data in any way. And then we can verify everything that comes after the rest of a program under this assumption. All right. So this is the basic idea. And this allows us to verify many programs that currently can't be verified modularly already. But it turns out we can do better. And I'll show you again on a slight variation of the example from before. So now our shared data structure is no longer just an integer. It is a list. And instead of just adding to the integer, so the loops are unchanged, but in the end, instead of atomically adding to the integer, both threads append to the shared list. Now, according to what I've told you so far, we would not be able to verify this program because appending to a list in general does not commute, right? And if you think about the state of the list after all concurrent modifications, depending on the secret value, we might have 6.7 or 7.6. So we actually shouldn't leak it at that point. However, if we look at the last line, we're actually sorting the list before returning it. So this program is actually safe in terms of its return value because we always return the list 6.7. So obviously we would like to be able to verify this. But commutativity here doesn't hold for the reason I've told you. So our second key idea is that we can weaken our commutativity requirement using an abstraction. So we only require a commutativity modulo abstraction. In this case, what we're observing here is that the secret-dependent order can, in fact, influence the contents of the list, but only the order, not which elements are in there. Right? It's 6.7 or 7.6. And that means we can here pick a multiset abstraction that essentially abstracts away the order of elements in the list. And with respect to this multiset abstraction, appending to the list actually commutes. It doesn't commute in general, but appending just adds a thing to the multiset, right? The order doesn't matter for this abstraction. So now I've shown you the basic proof obligations. Now how do we have to adapt them? Well, we basically add modulo abstraction everywhere. So we initially prove that our shared data structure has the same initial value modulo abstraction, that the updates commute modulo abstraction. Like in the case I just showed you, we can slightly weaken the same updates requirement, but I'm not going to go into the details there. That's a bit more complicated. And then in the end, after all concurrent modifications, we get to assume that we now have the same final values in both executions modulo abstraction. So for this example, that means if we pick a multiset abstraction after all concurrent modifications, we know that the multiset view of this shared list is does not depend on secret data in any way, and that is sufficient to prove that after sorting, which removes the secret-dependent order, we can leak the list. Now the entire list contents don't depend on secret information anymore. Okay. So I've already mentioned we formalized this in CommCSL. That's a relational concurrent separation logic. Relational because it always reasons about these pairs of executions of the same program. Because it's a concurrent separation logic, it allows thread modular reasoning and of course supports mutable heaps, but it has built-in support for this information flow reasoning based on abstract commutativity. And we've taken this logic and formalized it in Isabelle Hall and proved it sound. We've also implemented it in a tool called HyperViper. So that's an automated SMT-based verification tool based on Viper NC3, that's the name. And like other automated verifiers like Dardinier or Viper itself, for example, users have to provide specifications like preconditions, loop invariants, and also some things specific to our approach like the abstraction, and then the verifier either proves it correct or reports an error. And the tool is open source and available on GitHub. So very briefly, we have an evaluation where we just show that this approach is actually able to verify programs implementing a number of reasonable use cases, and in particular that this added notion of an abstraction really helps us to be able to verify more examples than we could otherwise. All right, So to conclude, we've presented a new technique for modular reasoning about the value sensitivity of concurrent programs. The key point is that it's independent of timing reasoning. Therefore, we don't also have to assume anything about timing behavior of the hardware, and so we are sound on any real hardware. The key idea is to use commutativity modular abstraction as a reasoning principle. We formalized this in a logic and proved it sound in Isabelle and automated it in HyperViper, and both of these are available online and also part of the artifact. Thank you.
Questions?
I'm Joseph Tasserati from NYU. Thanks for a very nice talk. So in your examples, you're using like the parallel execution construct. I'm curious, how does this work if I'm using forking, right? Because then I don't know necessarily that the other thread is ever going to finish, for example, if it's being starved.
Right. So in the logic, we actually only support like the parallel composition operator, but in our implementation, we do support fork and join statements. And what happens is basically that this assumption that now the contents of the shared data structure are non-secret, and you may now assume that you may now leak them. Basically, you only get this after joining all relevant threads and then after unsharing the data structure.
Okay, so I need like to have a barrier and wait for
Yes, basically if you want to do something before joining threads, then you would need something like a barrier, which our logic doesn't directly do, but which would be an obvious extension, yes.
Cool, thanks.
Hi, thanks for this great talk. Really enjoyed it. My question is about how you said that you can essentially ignore the timing information, but in the example that you showed where you're saying return sort of the list, that sort function itself might contain a side channel and likely does. So I'm wondering if there's some way to maybe compose what you're doing with an analysis that takes into account timing channels, or how those things relate.
So yes, the sort function's runtime might leak information via its timing, but also the left thread might, right? If like age is 2 million or something, the left thread will just take forever, and you can see something about the timing. You can conclude something about the secret from the timing anyway. So we're just not proving that. Our approach is really for, if you care about values, you can use this, and it makes things easy because you don't have to worry about timing. And then in cases where you also have to consider timing, then basically you can see that almost as like an orthogonal step, and you use a different kind of analysis.
Okay. Great, thank you.
Hi, this is Umang from NUS. Great talk. So my question is about the abstraction for commutativity. Do you automatically infer these abstractions, or you look at the program and then sort of understand?
No, so we asked the user to give us, so both in the logic and also in the more automated tool, we asked the user to give us some properties of the shared data structure, including the abstraction. And then what we do basically is, so that includes the abstraction and, for example, which operations are allowed on that data structure. And then we can prove in a simple way that doesn't require enumerating lots of interleavings, for example. We can prove that these operations actually commute modulo this abstraction, and then use this in the proof. But this is something that maybe could be inferred in future work. We've thought about this, but not for too long, but we're currently not doing.
So what are some other examples of abstractions that might be useful here?
So another thing is, so lots of the examples we have are, for example, things in maps. So my running example before was going to be, we have a map and we put things into the map, and putting doesn't commute because you override values, right? But it does commute with respect to the key set, for example. So if I then only leak the keys in the end and not the values, then that's fine. Or you can use these abstractions to do quite interesting things. So we have these producer-consumer examples where we're actually not abstracting the actual value in the like kind of shared queue that contains the tasks at all, but essentially we're abstracting away anything except like ghost state, that is like the sequence of produced or consumed items. So it's quite flexible and you can do a lot of things. But for like a lot of later structures, like for lists, multisets, means, lengths, sums, all of these things have useful applications.
Thank you.
Hey, Marco Guarnieri from India Software. Very nice talk. So I was wondering, you presented all these alternative approaches, like, making sure that secrets do not influence execution time. And, one of the advantages of these alternative approaches is that they can be boiled down to very simple rules for programmers, right? Oh, just make sure that secrets don't go into contraflow statements. And I was wondering if your approach, can you actually come up with simple rules for programmers?
These are the rules. I'm not sure if you consider them simple or not, but it's so maybe there are like you could abstract them to like something that's a bit more broad, but simpler. I mean, you can also just instantiate them for specific things, right? With maps, you're allowed to do this kind of thing. With lists, you're allowed to do this kind of thing, or these kind of things. Usually you have different choices of abstraction per data structure. But in principle, it's this, and then I haven't thought about whether to make it, how to make it simpler.
Okay, thanks.
I thank the speaker again. So.